So before we get to mechanism synthesis, we need a way to decide whether or not the mechanism we're going to synthesize is going to operate well. And there's quite a few different ways to do that. And the first one we're going to start off with is geometric inversions. And the nice thing about geometric inversions and a couple of the others that we're going to talk about momentarily is that all of these are based on a static analysis of the mechanism. So I can purely look at it from a kinematic drawing perspective and decide, is it going to function fairly well or not? So we'll start off with geometric inversion. That will lead us to a discussion of a toggle position as well as branch and circuits, and we will then move on from there. So starting off, geometric inversion. The idea of a geometric inversion is that if I take a mechanism, I have two different configurations of that mechanism for the same location of the input link. So imagine that this gold link right here is my input link. I have a coupler and the black link is my output link. And I have two different configurations. I have what we call the open configuration, and then I can have this gold link in the same position, but now be in this cross configuration. So I can branch between this inversion and this inversion here. So I have two different branches and I'm branching between them. So that is the idea of geometric inversion, two different configurations of the mechanism. Now, why is this an issue? Well, we have to pay attention to it because when we do our synthesis, our mechanism can either be on one of the inversions or the other one, and we won't know from the moment we start. So for the 4-bar that I've shown you here, we have what we call a reflection line that moves through the moving pivots B and the ground pivot C, the ground pivot D. And we can then flip links 3 and 4 over that inversion line or over that reflection line, and this would be the alternative inversion of the mechanism. So every 4-bar mechanism has a geometric inversion. Now imagine that I take this mechanism and I take link 2 here and I start to rotate it in the counterclockwise direction. As I move that farther and farther, you can imagine that these two branches start to approach each other and approach that reflection line. As we do that, we get to what's called the toggle position or the dead center position. And here you can see that links 3 and 4 are collinear. When this occurs, now, again, going back to this mechanism, now this gold link really can't control whether or not I'm going to be going to the open branch or the crossed branch. So I no longer have control of my mechanism from the input link because these two links are collinear. So this becomes a challenge. Why is it an issue? Well, one is the mechanism can lock up in that configuration if we don't have something else to help it through that toggle position. And we can also branch to alternative motions that we don't expect. So let's say that we're expecting to be on the open circuit. Well, we might accidentally cross over or move over to the cross circuit and not be creating the same motion that we want to. All right, so we've talked about this dead center condition. Now, how do we apply it? How do we use it? Well, as I mentioned, all mechanisms have geometric inversions. I've got two different mechanisms shown here. Both of them do have geometric inversions, but as I think about how do I get to that geometric inversion, we're going to say, can I pass through the dead point to get there or not? Now, the mechanism on the left here, this one has a dead center condition that I can cross through to get from the open inversion to the crossed inversion. Now, the mechanism on the right over here, I actually have to pull this pin joint out and reassemble it in the inverted state. So we're actually not able to pass through that dead point condition. So we differentiate these two and say that the one on the left, we have a single circuit and we're moving between two different branches on that circuit. And the one on the right, we have separate circuits. So both of our inversions are in different circuits. We have to take the mechanism apart, pull the pin, put it in the other inversion, and put the pin back together. Both of these can cause issues for us in the fact that when we synthesize a mechanism, the synthesis process does not pay attention to which inversion we're on. So we could have a few of our precision positions on one of these inversions while one of the positions happens to be on the other inversion. Now, 4-bars are not too bad. We really just have this one inversion to deal with. But as soon as we get up to more complex mechanisms, say a 6-bar, now we can have up to 6 circuits with a 6-bar mechanism. And each of these can have 1 or 2 branches, and it's very challenging to identify each one of these circuits. So when we're synthesizing these more complex mechanisms, we really have to pay attention to whether or not all of our positions are on the same branch and circuit. Now, there are some synthesis tools that we'll use later on called solution rectification, where we can pay attention to whether or not we're on the same circuit, but we'll get to those later in the class. So as a quick review of what we talked about, we can have any mechanism have different inversions. These are geometric inversions, where we're basically either able to pass through a dead point condition, where we now are branching, or if we have to pull that pin and reassemble it, now we have two different circuits for the mechanism.